And we can think of them as having multiple central atoms. And we just simply talk about the molecular geometry around one central atom at a time. So here, 1, 2, 3 carbons in a chain, looking at this particular molecule. I can talk about this central atom. It looks like 1, 2, 3, 4. 1, 2, 3, 4 electron domains. So we call this one a tetrahedral. Here, the center here, 1, 2, 3, this central atom has 3 electron domains. Notice they're drawn in a double bond. But 1, 2, 3 electron domains. So around here, this would be trigonal planar. And this central atom has only 2. It is a bent molecular geometry. And what you're not seeing here is the 2 oxygen pairs. So really this is 4, 2, 2, giving us bent oxygen with 2 that are bonded, 2 that are non-bonded, giving us a bent molecule. So the purpose of this slide is to remind you that even large molecules, we still only consider one region of the molecule at a time. Here's methanol, CH3OH. The molecular geometry around the carbon would be tetrahedral. It has 4, 4, 0. Here's the oxygen. Oxygen has 4, 2, 2. 4 electron domains, 2 that are bonded, 2 that are not bonded, giving us a bent molecule. 2 central atoms, 2 different answers for the molecular geometry. Yet another example of a large molecule called glycine, one of our amino acids. We have nitrogen, 1, 2, 3 that are bonded, 1 non-bonded, so the molecular geometry here would be 4, 3, 1, trigonal pyramidal. Here's carbon, 1, 2, 3, 4, 4 that are bonded, all 4 geometry here, so tetrahedral, 4, 4, 0. This carbon has 3 electron domains. 1, 2, 3 are bonded, 3, 3, 0 gives us trigonal planar. The oxygen, 4 electron domains, 2 that are bonded, 2 that are not bonded, giving us a bent molecular geometry. The pattern is the same. Each area of the molecule has its own unique molecular geometry. You cannot be asked for the entire structure with one correct answer. You turn the video off a moment, pause, and predict H3BO3. Find the molecular geometries. When you're ready, you started the video back up and can see the next slide. We have boron in the center. We have an OH group here, an OH group here, and an OH group up top as well. So boron serving as the central atom. H3BO3, the O's and the H's attach back. So here, boron is trigonal planar. This is the boron, central atom, 1, 2, 3, so its electron geometry look like 3, 3, 0. The oxygen's all created equal. Remember that there's lone pairs of electrons, so this goes back to 4, 2, 2, a bent molecular geometry. This one is bent, this one is bent, this one is bent, with 4, 2, 2 overall. So the structure here of boron is the central atom, and then 3 equal subgroups coming off of that central atom. For molecules to be polar, it must have polar bonds, which means that there's electronegativity difference. The bond has dipole moments, which means there's an unequal sharing of electrons. Perhaps the easiest way to recognize if a molecule is polar is by looking at its symmetry. If I look at a molecule and it is not symmetrical, in other words, I look in every direction of electron domain, and if something is unique, it's a polar molecule. If it's perfectly symmetrical, we know it to be a non-polar molecule. Thinking really in terms of symmetry makes polarity prediction quite easy. If I look at a molecule such as HCl, it's a linear molecule. It's only two dots connected by a straight line. But chlorine is more electronegative than the hydrogen, making this a polar bond. The hydrogen is barely hanging on to the chlorine in this covalent bond. It's just an unequal shared pair. Little positive sign at the end of this arrow shows the direction of the electron pull, leaving hydrogen partially positive and the chlorine partially negative. And we can see the electron distribution of this molecular pair, leaving a partial positive on the hydrogen with a low electron density, a partial negative on the chlorine with a very high electron density. And these are probably colored in our actual PowerPoint, showing red coming from green over here. We could definitely see a polar molecule. If I have a linear molecule in which I have two identical polar bonds, it's going to be a nonpolar molecule. If I have a molecule with a bent geometry, it will end up being polar. If I have a molecule in a trigonal planar molecular geometry, nonpolar, they all cancel out. Tetrahedrons are nonpolar if all of the ligands are exactly the same. Trigonal pyramidal will have an exposed pair of electrons at the top, making it a polar molecule. So molecular polarity in terms of symmetry. If I have a carbon with only two electron domains, as in carbon dioxide, the carbon in the center is being equally pulled toward the oxygen in each direction, creates a perfectly symmetrical molecule. Carbon dioxide is a non-polar molecule. The colored version of this slide might do a nicer job to show an equal distribution of the electron cloud around that central molecule there. So carbon dioxide, non-polar. Two electron domains, both heading into the same direction equally, creates an equal pull. Water, however, is a bent molecule. It's bent because the electron domain went 4, 2, 2. 4 electron domains, 2 bonded, 2 non-bonded. There's electron clouds up here. If I look up, I see electrons. I look down, I see hydrogens. It is not a symmetrical molecule, so it creates an area on the oxygen that's mostly negative, leaving the hydrogens partially positive. A bent molecule is a polar molecule, the dipole moment being pulled towards the electron cloud, leaving hydrogens with a net positive and oxygen with a net negative electron density. Predicting the polarity of molecules. Draw the Lewis structure and determine the molecular geometry. Determine whether the bonds in the molecule are polar, and again, that's by electronegativity difference. To be honest, here's as easy as this. If I have like elements, fluorine minus fluorine, the electronegativity difference is 0. It is nonpolar. If I subtract any other two elements that are not the same, I'm going to get a small electronegativity difference. Determine whether the polar bonds add together to give a net dipole moment. Think symmetry. Predict whether ammonia is a polar molecule. Once I draw the Lewis dot structure for ammonia, I can simply go, oh, not symmetrical. I have a pair of electrons. If I look left, right, and down, I see hydrogens, but I'm looking north, I see electrons. It's not symmetrical. This would be a polar molecule. Electron domain is 4. 3 are bonded, 1 non-bonded. When I have 4, 3, 1, I create an electron repulsive force on the top